In section 6.2, we're going to look at another integration technique called integration by parts. Again, we have integrated by reversing the basic rules of derivatives. That's what we did earlier when we found antiderivatives. In the previous section, we looked at substitution, and that was a reversing of the chain rule. In order to undo a chain rule, we utilize substitution. Integration by parts is basically the reverse of the product rule. It's not precise because this statement is not precise, because what we're really going to do is reverse part of the product rule. So integration by parts is essentially like reversing the product rule. Let me be more specific. Remember what the product rule said. The product rule said that if you take the derivative of the product of two functions, what you can do is take the derivative of one times the normal other plus the normal one times the derivative of the other. If we have capital F of x equals to x to the fourth times sine x, when we use the product rule, what we did is we took the derivative of x to the fourth, that is 4x to the third, we multiplied that times the normal sine of x, and then we added normal x to the fourth multiplied times the derivative of sine. Derivative of sine of x is cosine of x. That is the product rule. Now, what integration by parts is going to do, it's going to take one of these components, either the 4x to the third sine x or the x to the fourth cosine x, and it's going to integrate one of those pieces. Let's try reversing the product rule. The product rule is taking a derivative of a product of two functions. I will call those lowercase f and lowercase g. And it says if you take the derivative of f times g, you get f prime times g plus f times g prime. If I integrate both sides of this equation, taking a derivative and then integrating gets me back an f times g. In other words, integrating undoes the derivative. If I integrate the right-hand side, I will have to integrate both pieces of the right-hand side. In other words, both terms. I'll have to integrate the f prime times g. I will also have to integrate the f times g prime. Now, this is almost true. One thing I do have to worry about is when you integrate, you have to add a plus constant. It turns out that we can do that at the end, so I'm going to ignore that for now. Let's focus on this piece of integrating the product rule. If I want to figure out how to integrate f prime times g, I can simply solve this equation for this integration. What that would force me to do is subtract integrating f times g from both sides of the equation. When you do that, you get that the integration of f prime times g is equal to f times g not integrated minus the integration of f times g prime. That is integration by parts. That statement is essentially the formula for integration by parts. We do have to be a little bit careful. We have to make sure that f and g are both differentiable functions of a variable x on some interval. And then on that interval, we have this. If you want to integrate f prime times g, you can do it by taking normal f times normal g minus an integration of f times g prime. You might say, well, why did this help us at all? Because we're transforming a thing with an integration into another more complicated thing, which also involves an integration. The answer to that is hopefully this integration on the right is much easier to do. Or we can simplify it using a rule we already know. This integration by parts formula is something you'll want to write down and have handy throughout this section. Now, there's lots of instances in which integration by parts can be used. We're going to focus in this class on 3 main instances. Again, these are not the only 3 where integration by parts can be used, but we're going to focus on these 3 instances. When we have a polynomial function or a polynomial expression multiplied times either a trig expression or an exponential expression, a lot of times we'll want to use integration by parts. Number 2, if we have a polynomial multiplied times a logarithm, then a lot of times we'll use integration by parts. And then lastly, if we have an exponential expression multiplied by a trig expression or a trig function, then we'll want to use integration by parts. Again, these are 3 scenarios in which integration by parts will work. Obviously, I'm oversimplifying what's going to happen. Not every time you have a polynomial and a trig function will integration by parts be applied. Sometimes there'll be easier methods and so on and so forth, but integration by parts is nice in that case. You'll notice that in each of these, we have 2 different types of functions being multiplied. Whether it's a polynomial times a trig or an exponential, a polynomial times a log, or an exponential times a trig, there are 2 different types of functions being multiplied. And integration by parts does this well. Let's take a look at an example. We're going to use integration by parts to integrate the following. We want to take the integral of 4x times e to the 5x with respect to x. In this case, notice that 4x is a polynomial and e to the 5x is an exponential function. This tells me I want to use integration by parts. So I want to use integration by parts, but before I do that, I want to show you that substitution would not make this problem any better. Let me go ahead and show that. If I were to try substitution like I did earlier, maybe I would guess my u is 5x. If I take the derivative, I get 5. So my differential exchange would be du is equal to 5 times dx. Another way to write that is 1/5 du can replace the dx. Notice that if I try to do substitution here, the dx gets replaced with a constant times du. I'm going to put the 1/5 out front. The 5x can be replaced with a u. I guess I can replace this x as well by solving this equation. 1/5 u equals x. So I can call that x 1/5 u. Again, I'm going to pull that constant out front. 1/5 times 1/5 is 1/25. Notice that my expression really didn't get any simpler when I did substitution. I still have a polynomial times e to a power, which I don't know how to integrate there. So this shows that substitution really doesn't work on a problem like this. So what we need is we need to go back to our formula. All I'm going to write is integrate f prime g is equal to f times g minus integrate f times g prime. All of this will be with respect to x, obviously. We see here on the left-hand side, we have an f prime and a g. We also have 4x e to the 5x. In this formula, we need to determine what piece is going to be the g and what piece is going to be the f prime in our original expression. Because this is the polynomial times exponential function, what I want to do is call your f prime e to the 5x. Then call g the polynomial. In this case, that's 4x. In other words, if I have this situation where I have polynomial times e to a power, the polynomial is always going to be the g part, and the e to the power is always going to be the f prime part. We'll see that reason in just a moment. If your derivative is e to the 5x, then to get back your original function, you take an antiderivative. The antiderivative of e to the 5x is 1/5 e to the 5x. You could have added plus c right now if you'd like, but it's actually easier if you pretend the c is constant. That plus c will get canceled out when you actually go through this. So let's let the plus c be a constant of 0. Now we do the exact opposite direction on g. Going from g to g prime, I have to take a derivative. The derivative of 4x is 4. Notice one of these I did an antiderivative, and one of these I took a derivative. Be very careful on that. Now I have every piece that I need for this formula. So this formula says f prime times g, that f prime is e to the 5x, multiplied times g, g is 4x. Obviously, I'm going to integrate with respect to x, is equal to f, which is 1/5 e to the 5x, times g, which is 4x, minus f, 1/5 e to the 5x, multiplied times g prime. G prime here is just 4. Obviously, we're integrating with respect to x. I'm going to clean this expression up just a little bit and simplify it. 1/5 e to the 5x times 4x. I can call that 4/5 x times e to the 5x. That's just a little bit simpler after you multiply that. 4 times 1/5 gives you 4/5. We got an x, and then we got an e to the 5x. In this part, I'm going to pull this 1/5 and this 4 out front because they're constants. When you multiply 4 times 1/5, you get 4/5. Notice what happened to this integration on the right. This integration on the right is something that I know how to do. It's just e to a linear power. That's why I chose the g the way I did. Because when I took a derivative, I got a constant. And anytime I have a constant, I can just pull that constant out front of an integration. Therefore, this expression can be integrated, or that second half. Notice there's no integration needed on the first part. I simply need to integrate this second part. If you integrate e to the 5x, you get e to the 5x. And then you take your 5 and you divide it by, or you divide the coefficient by that 5. If you divide 4/5 by 5, you end up with a 25 in the denominator. And then at the very end, because we've integrated, we need to add on a plus c. And so what we're saying is that an antiderivative of 4x e to the 5x with respect to x is 4/5 x e to the 5x minus 4/25 e to the 5x plus c. That's how we do integration by parts when we have a polynomial times an exponential function. We let the exponential function be the f prime. We let the polynomial be the g. Remember, when you go from f prime to f, you do antiderivative. When you go from g to g prime, you do derivative. By the way, what's going on here is essentially this. We have a function here, and I'm just going to use this function to check that I got right. I have an expression here. Let's just call this expression whatever. And let's take the derivative with respect to x of this whatever expression. If I do that, what's going to happen on this first part is I'm going to have to utilize the product rule to take the derivative of this first part. When I do that, what happens is the polynomial would just become 4/5 normal e to the 5x plus normal 4/5 x multiplied times derivative of e to the 5x. Derivative of e to the 5x is e to the 5x times 5. When you multiply this 4/5 times 5, you get 4. And then you move on to the next term. The next term does not need a product rule. It can just be taken derivative directly. We take 4/25. Derivative of e to the 5x is e to the 5x times 5. If I take 5 times 4/5, I get 4/5. And then the derivative of a constant is always 0. Notice what's happening. Of these three terms, this term here is canceling out with this term here. And you're just left with the 4x e to the 5x as the derivative of this function, which means this function is the integration of 4x e to the 5x, which is exactly what we just said here. The answer that we're looking for is this one. And again, what I'm doing there is I'm just showing you what's happening. You're getting two pieces from derivative of the first part, and one of those pieces is going to cancel with the derivative of this part. Let's do another example. We're going to once again use integration by parts to integrate. This time, instead of having a polynomial times an exponential function, we're going to have a polynomial times a trig function. This is going to work very similarly to a polynomial times an exponential function. The most important part is matching up this integration to our general rule. Once I've matched up the f prime and the g correctly, then the process kind of falls into place about getting this part. Just like before, the polynomial, I'm going to make my g. That way, when I take a derivative of the polynomial, it's just a constant. The f prime I'm going to set as cosine of 8x. When I integrate cosine of 8x, the integration of cosine is sine, so I get sine of 8x. Because the argument in there is a linear piece, I just need to divide by 8 out front. 1/8 sine of 8x. This means this integration, the integration of f prime times g, actually let's replace it here. In this case, f prime is cosine of 8x. G is 2x. I'm going to put that in front just to make it look a little nicer. And we're integrating obviously with respect to x, is f times g. F is 1/8 sine 8x. G is 2x. Now that's multiplied times 2x. I'll simplify that in a moment. Minus normal f times g prime. Normal f is 1/8 sine of 8x times g prime, which is 2, integrated with respect to x. Let me clean that up a bit. The 2x, remember, is being multiplied. The 8x is in the argument. 2x times 1/8. Well, 1/8 times 2 is 1/4. So I get 1/4 x multiplied times sine of 8x. Again, if I take 2 times an 8th, I get 1/4. I can pull that out front. Now you see we're integrating sine of 8x. That's very much doable from the rules that we've learned earlier. So this integration of sine of 8x, the integration of sine gives me negative cosine of 8x. Because the argument is linear, the 8 is going to divide this coefficient. 1/4 divided by 8 is like 1 over 4 times 8, or 1 over 32. At the very end, I have to attach a plus c because we are looking for the integration. So I need the class of all antiderivatives, not just a particular one. And this I would probably clean up one more step. I would say that the integration that I was looking for, the 2x cosine 8x integration, actually became 1/4 x times sine of 8x. Notice this is a minus and then multiplied times a negative, so we're going to get a plus 1 over 32 cosine of 8x, and then plus c. That is my final answer. Just like last time, if you were to actually go about doing this, what would happen is that some things you'd end up with 3 pieces. You'd end up with 2 pieces from this part if you were going to take a derivative, and then you'd get a 3rd piece from that part. Let's call it P1, piece 1, piece 2, and piece 3. And then the constant would just give you 0. And one of these pieces, let's call it P2, would cancel out with the P3. And then this remaining piece would be the 2x times cosine 8x. I know that's a lot, but that's what's going on. So this is how you do integration by parts when you have a polynomial times either a trig function or a polynomial times an exponential function. Here's another problem involving a polynomial times a trig function. 10x times secant squared of x integrated with respect to x. You should use integration by parts to determine this polynomial, to determine this integration. Again, it's polynomial times trig function once more. Go ahead and push pause on this video and try it on your own. In the next video, I'll show you how this is done.